Welcome to this video lecture on the subject optical and microwave engineering. So in this lecture we are going to discuss about microwave semiconductor devices. So microwave semiconductor devices includes microwave diodes, point contact diodes, Gunn diode, impact triode and microwave transistors etc. So conventional transistors cannot be used at microwave frequencies due to some reasons. So it introduced some inductance and internal capacitance and high transit time. So transit time is the electron travel from one node to another node. So these are the reasons the conventional transistors and diode cannot be used at microwave frequencies. So we need microwave semiconductor devices. So for example, Gunn diode can be used at microwave frequencies. So let's see the Gunn diodes in detail. So it can generate the microwave signals around 1 gigahertz and possibly up to 100 gigahertz. It is also known as the transferred electron device. It does not possess any PN junction like a normal diode. So here we use a principle known as Gunn effect. So it is normally used for generating the microwave RF signals. It is also used as an amplifier. So they are easy to use and also low cost for generating the microwave RF signals. It is mounted within the waveguide to form a resonant cavity where it acts as an oscillator. So it is a transferred electron device because it has two electrodes. It does not contain a PN junction. So fabricated from a N-type semiconductor, and also materials used are gallium arsenide, gallium indium phosphide, and so these are the some of the special elements. So the device is simply an N-type bar with N plus contacts. It is necessary to use an N-type material. So because the transfer electron divide is only applicable to electrons. And central region is the active region, doped N-type gallium arsenide. So this is the construction. So it is a diode is a negative differential resistance device which is used as a low power oscillator to generate the microwaves. So here it is the characteristics of a Gunn diode. It depends on, it is a voltage controlled negative resistance. So in this picture you can see a graph which drawn between current and voltage. So it is a Gunn diode characteristics. So as the voltage increases, the current also increases. After a peak point, the current decreases. This region is known as the negative resistance region. So this is used for generating the oscillation. So device exhibits a negative resistance region on the VI characteristics curve. So this resistance area enables the Gunn diode to amplify the signal, enabling it to be used in amplifiers and oscillators. So however, it is the Gunn diode oscillators are most commonly used. So in this picture you can see the conduction band and valence band of the gallium arsenide. As the field increases, the electron drift velocity in gallium arsenide reaches a peak and then decreases. So energy of the electron increases and the electron can be scattered into the upper valley where the density of states effective mass is 0.55 m0. So this J.B. Gunn discovered the Gunn effect. So he observed some random noise-like oscillation when biasing the N-type gallium arsenide sample above some threshold value. So this sample can be used for generating the microwave signals. And materials which have the Gunn effect are gallium arsenide, indium phosphide, gallium nitride. Here must be direct band gap materials that have more than one valley in the conduction band, and the effective mass and the density of states in the upper valley must be higher than the main valley. So this will introduce the transferred electron effect in the sample. So here it should be biased in the negative differential resistance region to form the Gunn domain. So the electric field in the rest of the sample falls below the negative differential region and inhibit the formation of the second Gunn domain. So this produces the microwave oscillations. So to function as an oscillator, it can be placed in the resonant cavity It is comprised of two major components. One is DC bias and another one is tuning circuit. So generation of sustained oscillation is produced by the negative resistance property. Here we use tuning circuit. So the oscillation frequency depends on the middle active layer of the Gunn diode. However, the resonant frequency can be tuned externally. In case of electronic tuning circuit, the control can be brought about by using a waveguide or a microwave cavity or varactor diode. So in this diagram, we can see a coaxial cavity, and oscillations along the cavity is taken as the microwave output, and Gunn diode is fixed inside the cavity resonator. And during the negative resistance region, we can see oscillations are produced. So it is shown in this graph. And applications of Gunn diodes are, it is used as a low power oscillator at microwave frequencies and radar transmitters. And Gunn diodes can be built using semiconductors with very high electron mobility. So it is used as terahertz oscillators. Let's take the assessment. Gallium arsenide is used in the fabrication of Gunn diode because it has a less forbidden energy gap. And when the electric field applied to gallium arsenide is less than the threshold, the current in the material increases linearly. Thank you for listening this lecture.